Welcome everyone. The title of today's notes is Exponential Growth and Decay Models Day 2, and this in conjunction with the previous notes worksheet just meant to help you with the exponential function challenge that you're currently working on. And remember, you're allowed to use a partner with that, you're allowed to use your notes with that. A variety of exponential models that you're going to be working through, well, I should say problems that deal with exponential models. And so we'll take a look at some of the variations here today to kind of help you be successful with that. So we're going to dive right in. I just have a bunch of different examples. Each one is kind of labeled according to the variation, except for example 1, but I think this is a review problem. So let's take a peek. It says the amount of caffeine leaves the body at a rate of about 15.63% each hour. Suppose a cup of coffee contains 100 milligrams of caffeine. How much caffeine is left in the body after 8 hours? Sounds good. Well, in this case, I'm thinking before we go ahead and do part A, let's write a model for this. I think I'm going to try to find some space right in here. So for the amount of the caffeine, and remember something that increases or decreases by a constant percentage can be modeled exponentially. And in this particular case, I've got 100 milligrams to start. And then don't forget, everybody, it looks like we're going to have our exponential decay. Now remember, it's 1 minus the percent decrease. So I do probably want to pull off a 1 minus 0.1563 for this particular problem. And so I see that value, that decay rate, is going to be 0.8437. So make sure, just in case you're not sure where that number comes from, that it is 1 minus the percent decrease. So 1 minus 0.1563. And of course, we're going to raise that to the t, as we've been doing all along. And again, we've kind of done this before, where if I give you an input, you can give me an output, and vice versa. And so that's what A and B will be about here. So let's go for it, and I'll bring up, well, I won't bring up the calculator here. I think you can pull this one off. But basically, after 8 hours, so our t is designated in hours, so 0.8437, and then raised to the 8th. So again, we've had a lot of practice with this previously, and so hopefully this type of model works pretty well with it, for you. Excuse me. And it looks like I get on my calculator, as you guys are typing away there, I get about 25.67 milligrams. So according to this particular model, after 8 hours, there's still a little over a quarter of the caffeine left in your body. All right. Well, let's go ahead and do part C and just turn things on its head for a little bit here. In this case, I'm going to give you the output, the amount, and you'll give me the number of hours that have passed. So in this case, amount of caffeine decreases by half. So if we started with 100, I'm hoping everyone's okay with me putting a 50 right in there. So this is the model that we would be looking at. And of course, we want to go ahead and solve for that variable. And we've seen this now several times before, where the variable is part of the power. In fact, it's the exponent. But I probably want to go ahead and deal with that 100 first. So everyone, let's divide by the 100. I get my 0.5 equals 0.8437 raised to the t. And now, again, this is just that great algebraic step here. What I do is very simply I take that base of the power and I roll it on over to the other side. So there it goes. It's going to roll on over. And remember, when it rolls over to the other side, it changes from the base of the power to the base of the logarithm. So I get log base 0.8437 of 0.5, and that should be our t. And so I'm probably going to have to come up a little bit on this end right over here, but I'm going to ask you guys to calculate that piece and see if you're able to get the same number that I get. Essentially, remember, change a base formula if you have that TI-83, log of the inputs divided by log of the base. And if you solve this correctly, okay, so if you solve that correctly, then you should get a t value about 4.078 hours. All right, so good algebra there. We've got that piece taken care of. And so after about 4 hours there, it's decreased by half. Okay, so exponential decay model so far looking great. We've done the 2 parts there, inputs and outputs. Let's go ahead and do the part C that you see on the paper. And it says write the exponential model in base E. And remember what we basically talked about is that any exponential model in base B can be written in base E, and vice versa, of course. So the connection we had yesterday, and so let's rehash that piece, and this will help you again on that challenge, is that e to the k is equal to b. And in this particular case, it looks like I have that b value. That b value is 0.8437. And so that is our e to the k. Remember, e is our uniform base for the exponential model. K is, if you sort of think about it in terms of compound interest, we said is that nominal rate, that percentage before being compounded continuously. And so that's what we're looking for in this particular case. So I hope everyone's all right with taking that e and rolling that over to the other side. And when we do that, we should get the natural logarithm of 0.8437. And in this case, I think we kind of talked about it on yesterday's notes, but what happens with exponential growth in base e versus exponential decay in base e? Well, we should see a negative number unfold. So I'm going to do this one on the calculator to get a k value. And let's see, I've got natural log 0.8437, and look what happens. And the way this played out, where I saw this model, was written in base e, and should be about negative 0.17. Excellent. And remember, if k is positive, it's exponential growth, and if k is negative, it's exponential decay. So I'm going to leave it like that, basically, and we're going to write our model just off to the side. So we have 100 times e raised to the negative 0.17 t. And that looks good. Again, just two different ways to express an exponential model. As I told you, really, most of the ones that we'll be focusing on will be base B, based on the way I've defined it for you. But I like that connection between the two. All right, good little warm-up problem to get us thinking about it. And now what we're going to do is just different variations on the exponential model here and sort of scenarios that would occur. So let's see what I've got for you. Okay, so back at it here. Variations of percent increase and decrease. So this is the one that probably happens most frequently. And we've actually seen this before. So it says, given the initial value and an ordered pair xy of the two variable quantities. So just on your paper if you want, when we talk about the initial value, we are talking about little a. So in y equals a times b to the x, we're given the starting value, and then we're given some ordered pair relating the two variable quantities at some point. And the thing that we're going to solve for, of course, would be the b value, the growth rate or the decay rate. So this happens to be the example to my folks' home. And so here's what I have. A family bought a home in 1976 for $142,000. It was recently valued, and just so we're uniform here, everyone, this video is being made in 2012, so let's do 2012 there. So recently valued at approximately $1.3 million. Find the annual percentage increase for the home, meaning by what percent does the value of the home increase from 1 year to the next year to the next year to the next year. And really, when you ask for something along these lines right here for this piece, this is going to be our b value, because our b value is determined by 1 plus that percentage increase. So not a bad idea to put that in place. And then let's go ahead and fill in what we know and solve for what we don't know. So everyone, give me a y equals a times b to the x on your paper there. And as mentioned, this is a scenario where you're given the initial value. So everyone, I have $142,000 as the starting value of the home. I do not know what it grows by each and every year, so that's our b value. That is what we're going to find. And what we're looking for is the fact that the value is 1.3. And let's see, 24 and 12 after 36 years. So there's the match. There's the x and y, the ordered pair that would fit on this exponential curve. And if it's an ordered pair on the exponential curve, then we can use it in the exponential model. And so that's exactly what I'm going to do right here. I'll work through the calculations with you a little bit. I do think we're going to want to divide by that 142,000 first. So I'm hoping everybody is in agreement on that. If I do want this b value, I do need that piece. So everyone, I'm going to pull up my calculator. If you can do yours as well, that would be great. And let's see what we have. So 1,300,000, and then divide by $142,000. And so when we get that right there, I'm going to go out several decimal places there. If you're able to do a little more than what I can remember from this, that's perfectly fine. But I got about 9.1549. So 9.1549. Excellent. And actually, that would be the growth factor after 36 years. And the way we want to play this out, everybody, is to find the growth factor per year. And so in this case, I'm hoping everybody agrees, it is the base that we want. The base is the unknown. So no logarithm here. Let's be very clear about that. When the base is the unknown, that's when we're going to apply the root. And again, you see all types of roots, obviously, for these problems. In this case, it's going to be the 36th root of that number. So when we do the 36th root of both sides, we should get our growth factor for this particular problem. Let's see how it plays out. So if you remember how to do this on the calculator, you're going to hit 36, go to that math menu, and there's the x root. And let's see again, maybe I can get a few more decimal places in here. 9.154929.577. What the heck, I'll just put them all in there. And let's go ahead. As a matter of fact, sometimes you can just do second, here it is, second and then answer or entry down below. And unfortunately, it doesn't work on this calculator here. So I typed it in regardless, and I end up getting that piece. And so what I see is it's about 1.0634, give or take, as the growth factor, 0.634. And again, I just read the problem. That is our growth factor, absolutely. And remember that b value, which we just solved for, is 1 plus the percentage. So if I ask you for the percentage, again, these things go hand in hand. It looks like this would be 0.0634, or literally 6.34%. So on average, or annualized, the value of the home has increased by about 6.34% per year for 36 years. Okay, very nice. So you have little a, you have x and y, should be able to find b and write and use the exponential model. Okay, good one. So let's go on to the next variation that you see on your paper. It says, given the percent increase per time period, solve for the overall percent increase. So I guess here's the scenario that I see. Given the percent increase per time period, really, again, we're talking about b. So just above that piece, I would just write that, and that essentially will be our b value. From there, we're going to have to do, well, a little extrapolating, but I think we can pull this off. So let's take a look. Example 3. This just happens to be a fund that my wife and I invest in, and just did a little research on its return. So it says the mutual fund Fidelity Value has what's called a life annualized return of 9.45%. Using that value, by what percent would the fund increase in 5 years, and by what percent would the fund increase in 10 years? Okay, well, let's start this process out. Let's see what we know, and let's see what we need to fill in. So everyone, how about this? Y equals a times b to the x. And I guess the one thing that truly is given, probably the only thing as a matter of fact, is that b value. In each and every year, it's going up by 9.45%. So that is our b value as 1.0945. I hope everybody is okay with me writing that one piece into the mix. Now, it's going to say using that value, by what percent would the fund increase in 5 years and 10 years? So I think in just a moment, well, I'm going to wait just a second, but in a moment I probably will put a 5 years here, and then for the second part we'll probably put a 10 years there and so forth. All right. Well, here's the thing. You have no idea how much money we have invested in this particular fund, and to be honest, it really doesn't matter. We could have $1 in, we could have $1 million in, but when we're trying to find a problem like this, trying to solve that problem, that value is totally irrelevant. So what I would encourage you to do is just pick a value that makes sense to you. And what would be the easiest value to work on in terms of an initial value? Now, I would argue over the years, students have probably come up with one value more than others. So I would encourage us to use this. I would say either 1 or 100 works perfectly when we're talking about percentage increases and percentage decreases. I would encourage you to do 100. It works just as well, to be honest, if you start with $1. I'm going to start with $100 going in. Again, not that it matters. I think it's just easier to see with a value like this. So if I start with $100 and it's increasing by this amount every year for 5 years, now I can apply that. I guess the question then becomes, how much is in the account? So let's do that calculation together. And unfortunately, even after we get this, we won't be totally done. So let's see. I start with $100 and in times, and it's growing by that growth factor each year for 5 years. I hit enter, and I have that piece right here. So let's see about this, and then let's make a determination. So it looks like 157.06. So if I put in $100 into the account, after 5 years at this growth rate, it would go up to $157.06. Beautiful. Now, by the way, just one thing to note with this, people who don't know much about exponential growth would do something like this. And please don't do it on your paper. In fact, I'm going to erase it soon after writing it. A lot of people would say, oh, it's 9.45% per year for 5 years. So if I just multiply those together, I would get my answer. I would get the percentage increase over 5 years. Unfortunately, that is not correct at all. Because remember what exponential growth is all about, that idea of interest earning interest. We start taking 9.45% of a number after the first year, but then we take 9.45% of a larger number the next year, and then a larger number the year after that, and a larger. So you keep taking the same percentage of larger and larger numbers, so that's where the exponential growth comes into play. So it's actually going to be more than what 9.45 times 5 would be. I hope that makes sense. Now guys, what I can do with this is sort of resort back to just some middle school math and say, all right, well, what is the percentage increase from what I started? I'm going to give you a shortcut in just a second, but theoretically I would do this. The increase, new minus old, divided by the old, well, that would actually give me this right here, 0.5706, which happens to be 57.06%. That's just really, that is the algorithm that goes into a percentage increase. If you kind of look at it, because we started at $100, the shortcut to this, and trying to make a long story short here, is all I have to do is take this and subtract away the 100. And if I do that, notice, look at what I got here, my percentage increase. So if you can think back to middle school, you can do something like this to get the percentage increase. But starting with 100 just allows you to take your new value and subtract 100. And that actually is your percentage increase. It gained $57.06. So from 100, it's a 57.06% increase. Okay, good. I'm going to have to just come over to the left side here, and let's just repeat the process. So after 10 years, what would it be? And it's going to be more than just double that. Just be careful on that. So 1.0945, let's raise it to the 10th. So again, after 10 years, what would I have in the account? Let's bring up that calculator again, everyone. And let's see, I would do 100 times 1.0945 and raise it to the 10th. This would be the amount. If I started with $100, I would have $246.69. So 246.69. But I didn't ask for how much would be in the account if I started with 100. I asked for what is the percentage increase. And again, starting with that $100 just allows us to do this calculation quite a bit easier. So you can do exactly what I did over here if you would like. It is the exact same thing. That is how we calculate a percent increase. But the fact of the matter is, because we started with $100, all I really have to do, here's the shortcut, is take this and subtract 100. And so in this case, it looks like 146.69%. And you can see we've talked about this before. This is almost, well, it's between doubling and tripling. It's 2.5 times what you started with, starting with 100 and getting up to almost 250. And remember, between doubling and tripling would be in between 100 and 200%. We've seen that before. All right, good one. So in this case, Percent increase per time period, that's B. Pick a number to start out with and talk about the overall percent increase. Good problem. All right, let's go into the next. Also a good one. Now let's switch it. Another variation would be, what if I give you the overall percent increase? Could you solve for the percent increase per time period? There it is, everyone. Here's what I'm looking for. Now I actually want the B. So percent increase per time period is that B value. So my wife and I bought our first home, 1998 as a matter of fact, and sold it in 2004. And so after 6 years, it was at a price 60.58% greater than what we paid for it. And so what was the annualized return of the property? Now, one thing to note, again, students or people who wouldn't know much about exponential growth would say, oh, okay, well, this is the overall percent increase after 6 years. If I just want it per year, that would mean that I take 60.58 and divide by 6, end of story. But again, that's not how exponential growth works. Constant percent means you're taking a percent of larger and larger numbers, so it's not what I would refer to as linear growth. And so that's not the way to do it. But let's go ahead and see what we can do with this. Everybody, it starts with y equals a times b to the x. And it's asking for b, so I think that's the case. That's our variable. Everything else needs to be put in place. And that's what's kind of fascinating about this. 3 components are yet to be had here, and I need to put in numbers for each of those. I would argue 1 is pretty straightforward. You know it's 6 years. You know the time frame is 6 there, so that independent variable works out nicely. Now here's the thing. It's these 2 that are missing, the initial value and then the value after 6 years. You don't know that. In fact, I didn't give that to you in the problem. So x and y have to go together here, starting from an initial value. Well, you have absolutely no idea what we bought and sold our home for. So here's the nice thing about it, our flexibility with this. Choose a number. Now, obviously, we did not sell our home for buy our home for $100, but why not put it in place? It's an easy number to work with in this case. Start with 100 and then go from there. And so what I see in this case is if we started with $100 and it increased by 60.58%, then it really increased here by $60.58. The increase would translate to this over 6 years, from 100 to 160.8. And so you can kind of see that. That's why I personally, I like doing 1, to be honest, but the 100 really works just as well. Now the only thing is, this 100 is now going to be divided over, and I'm going to get b to the 6th is going to be 1.6058. So if we can get to that stage, I think we're in pretty good shape here. Good. Now we've done this calculation before. I do need this base to the power, so I'm going to do the 6th root on this and the 6th root on this, and then I think we should be in good business here. So let's see. I've got the 6th root. I'm going to hit the math menu again, and the 6th root of 1.6058. Hit enter, and there we go. And you can see that nice 1 plus the percentage there. I missed a couple of those numbers, but I'm just going to leave it like that. And as you can see, the annualized return. So basically, the home that we bought there increased in value by 8.2% every year for the 6 years that we owned it. Great. So different variations of percent increase and decrease. Really all good stuff. Let's try just the next 2, which go hand in hand here. So the last 2 that you're going to see would be the doubling and halving models. So I gave you a couple ideas to start. So things that double, we talked about this before, grow exponentially. So we're going to write exponential models for a quantity that doubles. We are, as it says, guys, we're going to be very careful with that exponent. So let's jump into example 5. It says a common inhabitant of human intestines is the bacterium E. coli. A cell of this bacterium in a nutrient broth medium divides into 2 cells. It doubles every 20 minutes. All right, there's our key. I'm just going to underline that piece just because it's jumping out at me. It's doubling every 20 minutes. and the initial population of a culture is 58 cells. So what we're going to do is write a function, again, for the number of cells, and that's going to be dependent on the number of minutes. And I think, yeah, this is going to be good. Alrighty, well, let's start it out here, everyone. You could do n for number, whatever you'd like there. Any variable, obviously, to represent the number of cells should be fine. And let's just play this out nicely, and then we'll talk about, well, when we hit the issue that we need to talk about, we'll stop for a sec. I would say, of course, you're starting with 58. It is exponential growth, as we said, because it doubles, and that's good. Now, something that doubles, we would say, obviously, we repeatedly multiply by 2. So it's going to be the base to our exponent. Again, something that doubles is repeated multiplication by 2. And so repeated multiplication is an exponent. And here is where we have to be a touch careful. So I'm going to do it wrong up there, and I need you to think about how to remedy it, how to fix. So if this was just, a standard model, we would take that base and raise it to the t. And that would tell me start with 58, and I want to apply this base to every time period. In this case, it would be minutes. But here's the case, everyone. If you look at the problem, it does not double every minute. That's what this would want me to do, to double it every minute. So how do I change or modify that exponent so it doesn't double every minute, but it doubles every 20 minutes? And if you think about it, the way to do that is to take that number of minutes and divide by 20. So we want to apply that base 2 exactly every 20 minutes. So now if you see this, and we'll write a couple things in here momentarily, if t is 20 minutes, then I've applied the base 2 once. 20 over 20 is 1. If t is 40 minutes, everybody, how many doubling periods would that make? Well, 40 divided by 20 is 2. So it would double twice. After an hour, 60 minutes. How many doubling periods would we have after 60 minutes? Well, 60 divided by 20 is 3. So by dividing by the doubling time, and that's the key, we now can apply that base 2 in an appropriate manner. Okay. Good. Well, I think now we can utilize this. Let's just do the algebra behind it. So this is how we do a base 2 model, but not doubling every minute, doubling every 20 minutes. So let's try this out. Input, output here. Here's 58. 2 raised to the, now just be careful, this I see 7 hours. So 7 times 60 should be 420. So this would be 420 divided by 20. And again, when we put that in the calculator there, we probably want to go ahead and put parentheses around that. But you could sort of think about this. In 7 hours, how many doubling periods would there be? Well, 420 divided by 20 actually happens to be 21. And that makes pretty good sense. There are 21 doubling periods in that 7 hours. And so we want to apply that base 2 exactly 21 times. So everyone, I'm going to go ahead and calculate what this is. I don't think I have it on my sheet. So I'm going to go ahead and just do 2 raised to the 21st. So 58, base 2, 21st. And as you can see, we've got a pretty large number there. So let's see if I have this on my sheet. No, unfortunately not. So I might have to go back and forth here, but I've got 1216. Caught a 34 there. Let's bring it back up for me. 34816. So put those in, and looks like up to 121 million. Yikes. And you can see just after a short time frame, and that's the power of doubling for sure. Okay, so given the input, just make sure you're in the right units. Come up with the output. Now let's switch gears. When will the population reach 20,000? All right, everyone, so it's time. Let's put in that output. 20,000 equals, let's do the 58, 2 raised to the t over 20. Okay, very nicely done. And again, just working through the math, I think everybody would be in agreement. We want to divide by that 58, bring it on over. So I'm going to do that up here. And let's see, I've got 20,000. 1, 2, 3 on that, divided by 58. And I might have to round a little bit here, but I've got about 344.8 344.828. 344.828 equals 2 raised to the t over 20. Okay, we're in a familiar position here, I think, everyone. Let's go ahead and take that 2. You know it's coming. It's the base of the power. Let's roll it on over to the other side. And so let's create a logarithm, base 2, of that 344.828. And when we do that, that would be equal to t divided by 20. So remember what that logarithm means is I go ahead and type this in. We're asking ourselves 2 raised to the what would give me that 344. So I'm going to do log of that 344.828, close that off, and divided by log of 2. And so we get that right there. I hope everyone's all right. This would be this piece right here. Let me just circle it. So that would be that aspect of it, about 8.4 and change. And then I hope you're all right with this. Let's deal with that 20 in one step here. And so what I'm going to do is go ahead and multiply by 20, and that should give me the number of minutes. So multiply that by 20, and I get 168.59. Hope you don't mind me taking care of that piece. And this would be in minutes if I remember the units on this. Okay, looking good. So given the output there, just solving a base 2 exponential equation, and just the only thing we haven't seen before maybe is just this t over 20, but in solving it we bring it on up. Okay, let's do the last one. So this is what's called halving, H-A-L-V-I-N-G. So something that divides in half on a consistent time frame, I guess. So let's see what it says. Half-life, and use base 1/2. Again, be careful with the exponent. And the context that we're going to see this is what's called carbon-14 half-life. So, my science is probably a touch rusty, but so let me just read what it says here, and then we'll check out example 6. So it says, living things constantly consume carbon through photosynthesis for plants and for animals' ingestion of those plants. The atmospheric ratio of carbon-14 sorry about that. The projector's on a timer and just shut off for a second, so had to reboot it, but I think I can pick up here. So I think we said something about the ratio of carbon-14 to regular carbon-12 remains consistent at 1 part per trillion. So if something is alive, 1 trillionth of its carbon atoms will be carbon-14. But once a plant or animal dies, its carbon-14 is no longer replenished, and carbon-14 is radioactive and unstable. And here's the key, everyone, with a half-life of 5,730 years, which means that half the atoms will turn back into nitrogen over that period, and that rate of decay is instrumental to gauging age. So that's what we're going to use, the radioactive carbon-14 half-life of 5,730 years, to take a look mathematically at a couple of carbon dating situations. So we're going to do one here together. You're going to do at least 1 or 2 on the exponential functions challenge, and some interesting stuff with this. So this is actually a cave in southern France, the Chauvet Cave. Actually, they made a documentary about this in 2011. I think it was called something like Cave of Forgotten Dreams or something along those lines. Pretty interesting movie about, I think, the oldest discovered paintings in caves. So let's see what it says here. So it contains some of the oldest prehistoric paintings ever discovered. Samples taken from torch marks and the paintings themselves were shown to have about 2.6% of the original carbon-14 present. Estimate the age of the paintings. Okay, well, let's go right into solving this. So in this case, let's get the exponential model ready to go. And I think what we're going to want to do here, everybody, is realize that the carbon-14 is decaying by half every 5,730 years. So we're going to use our base 1/2. Same thing, everybody. I'm going to do it wrong for just a moment, and then we'll fix it. So I would do my base 1/2 raised to the t, but this would say to apply this base 1/2 every year. I don't want to apply it every year. I want to apply it every 5,730 years. And so there we go again. That half-life becomes the denominator of our fractional exponent. So that's the case right there. And again, the scenario would be the quantity is irrelevant. It's the percentage that's calculated. And so in this case, at the moment of death, my understanding is there's 100% of the carbon-14. And then as it decays over time, that percentage goes down and down and down. And so what I see here in this particular cave, they found the carbon-14 that had about 2.6%. So you can see the x's and y's going together here. Some x value, some time value has passed in order to go from 100% to 2.6%. And that's how this model plays out. So let's go ahead and solve this. And by the way, let me repeat that just one more time. So t is missing, so the number of years that have passed, with a base 1/2 every 5,730 years. And what we're doing is going from 100% of the carbon-14 to 2.6% of the carbon-14. Well, let's go ahead and solve this together. Bring that 100 on over, and then t over 5,730. Everybody, it is time one last time here on this notes worksheet. Let's bring the 1/2 on over as the base of the logarithm. So 5730 here, and this would be log 0.5 as the base of 0.026 as that input. Let's calculate that, everybody. I'm hoping you understand that this is a number stored on your calculator. We just need to access that. And then how about we go ahead and multiply by 5730. Okay, I'll do those two steps if that's all right with you. I'm going to do my change of base formula on that as I have my 83 up here. So log 0.026, again, log of the input divided by log of the base, and I get that piece right there. And let's multiply by that 5730. And there we go. My understanding is that these paintings have been dated anywhere in between 30 and 32,000 years. I'm sorry, I lost that number. Let's get that back. But according to this model, about 30,170 years. Wonderful. All right. So some good variations on exponential models there. And again, this is kind of that culminating piece to help you with that exponential functions challenge. So try some of those out and then see if you can do some good applications on your own or with your partner. Thanks again for listening, of course. And if you have questions, just let me know.